Hello everyone, and welcome. Today, I'm excited to introduce you to the Bardenpho process, Advanced Biological Nutrient Removal. This presentation will explore a comprehensive 5-stage biological treatment system designed to achieve superior nitrogen and phosphorus removal in wastewater treatment plants. Over the next few minutes, we'll cover how this process works, its benefits, and why it's a key technology for sustainable water management. Let's get started. So, what exactly is the Bardenpho process, and why is it such a game changer? Well, it's a revolutionary treatment technology designed to handle wastewater more efficiently. Essentially, it's an advanced biological nutrient removal system that cleverly combines different treatment zones, anaerobic, anoxic, and aerobic, in a specific sequence. This carefully orchestrated process allows us to target and remove nitrogen and phosphorus more effectively. The reason this matters so much is because it was developed to meet very strict environmental discharge standards. That means we can treat wastewater to a level that protects our water bodies and ecosystems. And the key takeaway here is that the Bardenpho process isn't just about cleaning water. It's about doing it in a way that's both highly efficient and environmentally responsible, aligning perfectly with our overall goal of sustainable wastewater management. Let's start by looking at the core problem we're facing: nitrogen and phosphorus pollution in water treatment. These nutrients, while essential in small amounts, can become problematic in excess. When they build up, they lead to a process called eutrophication, which is essentially an over-enrichment of water bodies. This causes algae blooms that can be stunning to look at, but they come with serious consequences. As these algae die and decompose, oxygen levels in the water plummet, creating dead zones where aquatic life struggles to survive. Now, on top of this environmental challenge, we also face increasing regulatory pressure. Governments and environmental agencies are imposing stricter rules to limit the amount of nitrogen and phosphorus that can be released from treatment plants. This means we need more advanced and effective removal methods to meet these standards. Finally, beyond regulatory compliance, there's a vital need to protect our aquatic ecosystems. These ecosystems are delicate and vital for biodiversity, recreation, and even our economy. To safeguard them, we must develop innovative treatment solutions that go beyond traditional methods and are capable of effectively removing these nutrients. All of these points highlight the urgent need for smarter, more sustainable approaches in water treatment, which ties into our overall theme of advancing environmental protection through innovation. Let's walk through the process overview, which highlights the 5 sequential treatment zones. Starting with the primary anaerobic zone, this is where phosphorus is released from the biomass. It's a critical step because it helps in managing phosphorus levels effectively. Next, we move into the first anoxic zone, where denitrification occurs. This process is essential for removing nitrates from the water, transforming them into nitrogen gas, which escapes into the atmosphere. Following that, we enter the aerobic zone, where nitrification takes place. Here, ammonia is converted into nitrites and nitrates, and phosphorus is also taken up by the microorganisms, further reducing nutrient loads. Then, we have the second anoxic zone, providing an additional opportunity for nitrogen removal, ensuring that residual nitrates are minimized before the water moves on. Finally, in the last zone, which is aerobic, we perform residual treatment. This step ensures any remaining pollutants are addressed, leaving the water clean and compliant with standards. This entire sequence is designed to optimize nutrient removal through these carefully staged environments, which together form an integrated, effective treatment process. Now, let's explore stage 1, which is the primary anaerobic zone for phosphorus release, often called the foundation stage. In this stage, we operate in an oxygen-free environment, which is crucial for the process. Phosphorus-accumulating organisms, or PAOs, play a key role here. They actually release the stored phosphorus from their cells, which might sound counterintuitive at first, but it creates the necessary conditions for effective biological phosphorus removal later on. Since there's no oxygen or nitrate present, these PAOs consume organic carbon, which is abundant in the system. As they do this, the phosphorus they stored inside is released into the solution, making it available for removal. Typically, this retention time, meaning how long the wastewater spends in this zone, is around 1 to 2 hours. This stage is fundamental because it sets the groundwork for the subsequent steps in removing phosphorus efficiently. It's like preparing the environment so that when conditions change, we can effectively trap and remove the phosphorus, improving the overall process of wastewater treatment. Now let's look at stage 2, the anoxic zone for denitrification. This is where nitrate reduction happens. Basically, denitrifying bacteria step in to convert nitrate into nitrogen gas, and they do this by using organic carbon as an electron donor. This process is crucial because it helps remove nitrogen from the system effectively. Next, we have the mixed liquor recycle. The nitrate-rich mixed liquor from the aerobic zone is recycled into this anoxic zone, providing the necessary substrate for denitrification to occur. This recycling ensures that nitrate is continuously available for bacteria to process. Finally, the nitrogen gas produced is naturally released into the atmosphere. This step is vital because it permanently removes nitrogen from the system, preventing it from accumulating and causing issues like eutrophication downstream. Overall, this stage highlights the importance of biological processes in wastewater treatment, using bacteria to convert harmful nitrates into harmless nitrogen gas and releasing it safely into the environment. Now let's take a closer look at stage 3, the aerobic zone, which plays a crucial role in our wastewater treatment process. This zone is what's called a dual-purpose treatment area, meaning it handles two important functions at the same time. First, there's nitrification. Here, ammonia, which is a common pollutant, gets converted first into nitrite and then into nitrate. This transformation is essential because nitrate is much easier to remove from the water later in the process. At the same time, this aerobic zone supports phosphorus uptake. Phosphorus-accumulating organisms, or PAOs, absorb excess phosphorus from the water, which helps prevent nutrient pollution in natural water bodies. Additionally, this environment encourages biomass growth. Microorganisms thrive here, multiplying and becoming more abundant. This biomass is vital because it carries out the biological processes we're discussing. What's particularly important to highlight is that the aerobic environment provides the energy that PAOs need to uptake phosphorus. In fact, they can absorb far more phosphorus here than they released during the previous anaerobic phase. This efficient uptake is a key part of achieving overall nutrient removal in the treatment process. So, in summary, this stage not only helps us convert harmful ammonia into less problematic forms, but also actively removes excess phosphorus, all while supporting the growth of beneficial microorganisms. It's a vital step toward cleaner, safer water. Now, let's take a closer look at stage 4, which is the secondary anoxic zone for additional nitrogen removal. In this stage, we focus on enhanced denitrification, which is essentially an additional step where biological processes help reduce nitrates further. This is crucial because it allows us to remove more nitrogen from the wastewater, improving overall treatment effectiveness. The key here is efficiency boost. By adding this secondary anoxic zone, we're able to achieve higher total nitrogen removal compared to systems that rely on a single anoxic process. This means cleaner water and better compliance with discharge standards. Finally, this process also helps us fine-tune the nitrogen removal to meet specific discharge requirements. It acts like a balancing act, ensuring that the nitrogen levels are just right before the water is released back into the environment. Overall, this stage enhances the robustness and flexibility of our treatment system, making sure we meet environmental standards effectively. Now, let's look at stage 5, which is the final aerobic zone for residual ammonia treatment. This is often called the polishing step, and it's really the last line of defense to ensure our effluent is up to standard. This final aerobic stage plays a crucial role in making sure there's no remaining ammonia left in the water. It's about fine-tuning the treatment process to achieve the highest quality before discharge. One of the key processes here is ammonia polishing. Essentially, this step converts any leftover ammonia into nitrate. This conversion is important because it helps us meet strict discharge limits and avoid environmental issues. Another vital aspect is maintaining biological stability. By keeping a healthy microbial population, we prevent process upsets that could jeopardize the entire treatment chain downstream. Overall, this polishing stage ensures that the water leaving the plant is not only compliant, but also environmentally safe, tying back to our goal of sustainable and effective wastewater management. Now, let's look at some of the key benefits, applications, and considerations for implementing this technology. First, when it comes to nitrogen removal, we're achieving an impressive 95% efficiency in total nitrogen removal, which is crucial for protecting water quality. Moving on to phosphorus removal, we're seeing superior biological phosphorus elimination, with a 90% removal rate, helping to prevent algae blooms and eutrophication. Another significant advantage is energy savings. Our system reduces aeration needs compared to conventional systems by about 30%, which not only cuts operational costs, but also lowers the environmental footprint. As for key applications, this technology is well suited for municipal wastewater treatment plants, industrial discharge compliance, and nutrient-sensitive watersheds. It's also a great option for upgrading existing facilities, providing a cost-effective way to enhance treatment performance. Overall, these benefits highlight how this approach can effectively address nutrient removal challenges while also supporting sustainability and operational efficiency.